All right, we're up to class 70. The goal, I forgot to put it here, but it's basically to start looking at sound waves. All right, so let's see. Just to do now some stuff we've seen before. 4 waves hit the shore every 10 seconds. So right there, I know we can find the frequency. Frequency is number of oscillations or number of waves per amount of time. So our frequency is 0.4 seconds. Excuse me, hertz. We're also given another piece of information. The crests of 2 successive waves are 4 meters apart, so that's our wavelength. So if we use the equation V equals F lambda, we have our frequency is 0.4. Our wavelength is 4. And we get a speed of 1.6 meters per second. All right, so let's see. We did a simulation, just using some waves. The tuning fork vibrates back and forth really fast. How fast? A 256 hertz tuning fork vibrates back and forth 256 times every second, so way faster than we can see. The fork hitting the air creates areas of slightly higher and slightly lower pressure. So the tuning fork's literally hitting the air, causing it to bunch up and to spread out. So this is an image of what sound waves actually look like, but we find it much easier to depict them like a transverse wave below here, although that's not really what they look like. But the areas of high pressure right here line up with the crests. The areas of low pressure line up with the troughs. So these pressure variations go in all directions. These pressure oscillations transmitted through matter are sound waves. Sound waves require a medium to travel, just like any other mechanical wave. Sound waves are longitudinal waves. Since the particles oscillate parallel to the direction of the wave's motion. So it's not like a standing wave or the transverse waves like we saw in class, where the waves go up and down as they move left and right across the rope or across the spring. These are compression waves, where the sound is literally compressing and spreading out as it travels across the room. The speed of sound at STP, this is the number we're going to use on it from our reference table, is 331 meters per second. Why can't sound travel through space? There's no medium. There's no air, nothing. So both period and frequency only depend on the source of the wave. They do not depend on the wave's speed or the medium, right? The wave's medium dictates the speed, but the source dictates the frequency and the period. So just looking at a few practice questions here. The first one says the speed of sound at S2P is 331 meters per second, so I'll write that as my first given. What is the wavelength? If the frequency is 256 hertz. So we're going to use V equals F lambda. 300, and I'll leave the units out for now. 331 equals 256 times lambda. Divide both sides by 256. Let's see if we throw into our calculator 331 divided by 256. We should get about 1.29 meters. The next one says an 855 hertz sound wave moves through an iron railing at a speed of 5,130 meters per second. What's the wavelength? So again, just writing down our givens. Frequency equals 855 hertz. We're looking for the wavelength. And the speed of sound here is not 331, that's only in air at STP. Since we're going through an iron railing, it's a different number, in this case 5,130 meters per second. That number would not be on your reference table. So we start with V equals F lambda. Again, I'll just leave the units out to save some space and time. We have to divide both sides by 855, so 5,130 divided by 855 comes out to be exactly 6. The sound wave now moves into air. Which characteristic of the sound wave will remain constant? Like we said before, the frequency will remain constant, as will the period, but the frequency is the important thing for this next calculation. So calculate the new wavelength in air. So let's see, the frequency is the same, so that doesn't change. F equals 855 hertz. Now it's in air, so we know the velocity of sound in air is 331 meters per second. And we're looking for wavelength. So we have V equals F lambda again. V is 331. Again, I'm just leaving the units out, but you should get in the habit of using them for the exam. Divide both sides by 855. We have 331 divided by 855. Comes out to be 0.39. All right, so for this part, we're just kind of talking about what frequencies can people hear, which ones can't they hear. So we watched a couple videos. Pitch is the highness or the lowness of a sound. It's determined by the frequency of the wave. The volume depends on the amplitude. And it's important to note that frequency and amplitude are not related. By that same idea, pitch and volume aren't really related. And we measure sound level in decibels. The higher the decibels, the more sound there is. The decibel scale is a little bit tricky. It's a logarithmic scale. It's not linear, but that's not really important. All I want you to understand is that decibels are what we use to measure how loud something is.